Okay, we're going to review Unit 2, which is Forces. And before I start this video, I just want to remind you really quick that this video is going to take approximately 20 minutes from start to finish. However, before you watch the video, make sure that you have about twice that much time. You want to spend about 40 minutes going through this. If something didn't make sense, you're going to replay the video. You should be pausing it every time you try a problem. So although it's going to be about a 20-minute video approximately, it's going to take you longer if you're using the video in the right way to study. Okay. A force is simply a push or pull. That push or pull can be caused by a number of things. It can be caused by gravity, called the weight force. It could be caused by a stable object, a normal force. A spring can push or pull. Friction can actually push or pull. Tension, meaning a rope, a cable, a wire, a chain, anything like that. And these are the main forces in this unit. Now there's other forces that can push or pull, such as the electric force and the magnetic force, but we're going to leave those out, and we'll address those in later reviews. One thing I want to point out with friction is that kinetic friction, sliding friction, is always less than static friction, stationary friction. Okay, it takes more force to get something to move than to keep it moving. Other things to point out, tension is only a pull. Okay, I can't push something with a rope. That's pretty difficult to do. Also with tension, remember, one rope has one tension. Okay, at any point along a rope, it only has one tension. So once you find the tension in one place, you know the tension in every place in the rope. Okay. A big part of this unit is being able to draw precise, accurate free body diagrams. This is just a picture that shows all the forces, and it shows that you understand all the forces in the problem. Little details of the free body diagrams. They have to start at the center of mass, okay? And they must have arrowheads. Okay? Don't just draw a line. You have to have an arrowhead on your free body diagrams. This is how I would like you to label your free body diagrams. Weight is mg, in parentheses, weight. Friction is F of F, at big F subscript F, and then friction in parentheses. So we always do F of something, force of something, and then we write the full name in parentheses next to it. We never break forces into their components on the diagram. We save that for our working free body diagram. That's the one that we can get messy. The working free body diagram, we can get that messy. But when a problem says draw a free body diagram, we just draw and label the forces. We don't break anything into components. We just leave it nice and clean and simple. Okay, let's look at a couple free body diagrams. But before we do that, go ahead and pause the video. Try and draw these 3 free body diagrams as accurately as you can, and then play the video when you're done. Okay, you should have had a chance to draw your 3 free body diagrams. Here we've got a monkey hanging from 2 vines. So first off, the monkey has a weight force because I'm assuming the monkey's on Earth. Now there's 2 vines. The vines are kind of like ropes, so I'm gonna call these tension forces. And tension always goes in the direction of the vine. So I'm gonna try and make the force from vine B parallel to vine B. So this is F of T, tension, and this vine A has a different angle, so I'm going to try and show that it has a different angle on the picture. F of t tension again. And if you wanted to, you could label these tension A and tension B. Moving on, we've got a little mass, a little ball that's moving in a circular path, and I see in the picture that it says spring scale. There's a spring scale on this apparatus, but that really doesn't matter for the forces acting on the ball. All I look at is what is touching the ball. Okay, if the spring doesn't touch the ball, there's no spring force. Simply because the spring has to be touching the ball to exert a force on it. So start with weight, mg, weight, and it's connected to a string, and it says that the cord is not horizontal. So there's a slight upward direction, and that's F of t tension. They're calling it a cord, but remember, a tension force is from a rope, a cable, a chain, a cord, a string, etc. All of these fall under the tension category. Okay, last one. We've got a ramp, a pulley at the top, a couple masses. Two of them are sliding on the ramp. One of them's hanging off the other end of the string. We're drawing a free body diagram for mass 1 right here. So just like always, the weight force is pointing down. Now when I label this, I'm going to label this M1G, weight. It has a support force from the ramp. The ramp is stable, so we call that a normal force, F of n, normal. Now, it's moving with constant velocity down the ramp. Okay, this is important. If it's moving down the ramp, friction always opposes motion. So friction is pointed straight up the ramp. F of F, friction. Okay. You might even want to show here that your normal force is perpendicular to the ramp. You might even put a little right angle sign in there. Okay. Okay, Newton's first law. Sometimes this is called the law of inertia. The idea behind Newton's first law is this. When the forces are balanced, meaning the up forces equal the down forces and the right forces equal the left forces, another way of saying that is the net force is 0. There's only two possible ways to describe the motion of the object. The object is either at rest or it's moving with a constant velocity. Those are the only two possibilities. When the forces are balanced, the object is either at rest or moving with a constant velocity. In other words, in both of these situations, the acceleration is 0. Okay. If the object is at rest, we call this static equilibrium. And if the object is moving with a constant velocity, we call this translational equilibrium. So at rest is static equilibrium, constant velocity, translational equilibrium. Try these next two problems for Newton's first law. Go ahead and pause the video now. Okay, you should have attempted these two problems for Newton's first law. The first one reads, 3 forces act on an object. If the object is in translational equilibrium, which of the following must be true? So translational equilibrium means the forces are balanced, and since it's translational, the object is moving with a constant speed and direction. Constant speed and direction. So I haven't even read the choices, I'm just writing down what I know about translational equilibrium. Okay. The vector sum of the three forces must equal 0. That is absolutely true. Okay, that's like saying the net force is 0, and that's true. The magnitudes of the three forces must be equal. Magnitude means size. Okay, so does the magnitude of the three forces have to be equal? So here's one possibility. Let's say we had three forces, all separated by 60 degrees, and all the same force, 10 newtons, 10 newtons, and 10 newtons. Okay, that is definitely, those forces are definitely balanced. But is it possible to have three forces that aren't all the same magnitude? And I think it is. So let's come up with an example. So here's a force pointing straight down. Here's a force pointing up at a slight angle. Okay, and if I think about this force at an angle, it has two components. And to balance the up, I have a down, but to balance the right, I would just need a small left. So here's an example of three forces that are balanced, but they're not all the same magnitude, so I'm going to say that's false. All three forces must be parallel. I can clearly see here that not all the forces are parallel. An example of three parallel forces would be, say, 5 newtons, 5 newtons, and 10 newtons. So those are all parallel. That's one example. But do they have to be parallel? No, that's false. So one only. Let's take a look at the next example. We have a block of weight W hanging by 2 strings. And it's asking me, what is the tension in the string? I'm going to start out by drawing a free body diagram. We have a weight W, and we have 2 tensions. And since the angle is the same, I know that because of symmetry, both of the tensions are the same. Call them both T. Anytime I have forces at an angle, I'm going to break them into their components. Here's my angle theta. And I'm going to label the components. This is T sine of theta. This is T sine of theta. And inside is T cosine theta. Because I know that the object is not moving, the up forces equal the down forces, the left forces equal the right forces. The up forces are T cosine theta. So I have T cosine theta plus T cosine theta, one from each string, equals the weight, my down force. The left force is T sine theta, the right force is T sine theta. This doesn't tell me much. Okay, so I'm going to work with this equation. I have 2T cosine theta equals W, or solving for T equals W over 2 cosine theta. So there's the tension, or it looks like choice D. Okay, Newton's second law. Compared to Newton's first law, this is when all the forces are balanced. Okay, Newton's second law is when the forces are unbalanced. And Newton's second law essentially says that when the forces are unbalanced, an object accelerates. And unbalanced forces cause a changing speed or a changing direction. The equation F net equals ma. Sometimes I like to rewrite this: F net is up minus down equals ma, or right minus left equals ma. So give these next two problems a try. Newton's second law. Go ahead and pause the video now. Okay, you should have tried these two Newton's second law problems. Let's go through them. A ball falls straight down through the air under the influence of gravity. So I have some ball falling towards the earth. I know that it has a weight mg. There is a retarding force F on the ball with a magnitude given by bv, where v is the speed of the ball and b is a positive constant. So a retarding force, what are they trying to say here? If something was falling through the air, what would be retarding it? Air resistance. So I have an upward force of air resistance given by bv. I want to know what the acceleration is. So I'm going to write Newton's second law. F net equals ma. The net force in this problem can be expressed as down minus up. Plug in my forces. mg minus bv equals ma. I'm looking for the acceleration, trying to solve for a. So I'm going to divide everything by the mass. And these m's cancel, these m's cancel, and I end up with g minus bv over m, or choice B. Okay, let's try this second problem. We've got two blocks. We know their masses, and they're being pulled along on a frictionless surface by a force F. First things first, I need to draw free body diagrams. So the block on the left has a force little mg, that's its weight, and a normal force little n. I'm calling it little because it's a smaller mass, and it's also being pulled to the right by this string. I'll call it T. Being pulled to the right by T. The block on the right has a weight force. I'm going to call it big mg because it's got a bigger mass. I'm going to call the normal force big N. It's being pulled to the right with a force F, and this string is pulling it back to the left with a tension T. And so here's my two free body diagrams. What I need to do is write a Newton's second law equation for every mass in the problem. So I'm going to start with F net equals little ma, that's for this mass, and F net equals big ma, that's for this mass. Now I have the same acceleration for both masses because they're connected. Since they're connected, I know the accelerations must be the same. Okay, the net force of the small mass is simply T. And I'm going to go ahead and put its mass in. Its mass is 1. Okay. The net force of the big mass is right minus left, F minus T. And I'm going to put its mass in. It's 2. Okay. We're trying to find the tension, so I'm trying to solve for T. And I don't know the acceleration, that's an unknown. So what I'm going to do is, since T equals A, I'm going to substitute that for A in this equation. So I have F minus T equals 2 times T, or F equals 3T, and solving for T, T equals F over 3, or choice E. Okay, last page. Newton's third law. Big thing to remember with Newton's third law is that Newton's third law deals with two objects. Okay, and they're two interacting objects. And what Newton's third law says is that when two objects interact, they exert forces on each other that are equal and opposite. Or I like to say forces come in equal and opposite pairs. So this is like, you know, if you get frustrated, you're solving a physics problem and you get frustrated and you hit the desk, the force from your hand on the desk, let's say you hit the desk with 30 newtons down, the desk hits your hand with an equal and opposite force, 30 newtons up. So if you slap something, it slaps you back. Here's a problem. A weight force and a normal force are not an example of Newton's third law. Why not? Think about this, pause the video, and then replay. So why are weight force and normal force not an example of Newton's third law? Well, if I think about an object, let's say we have a block sitting on the floor. There's a weight force, there's a normal force. Why are these not examples of Newton's third law? They're equal and they're opposite, aren't they? Equal and opposite. The reason this is not an example of Newton's third law is we only have one object here. We're only talking about the forces on the block. Okay, if you want to talk about Newton's third law, you have to talk about the forces on two different objects. Okay, two objects. That's the key with Newton's third law. A very common type of problem in AP Physics are ramp problems. When we have a ramp problem, what we do is we tilt our coordinate system. We no longer have the y-axis and the x-axis pointing up, up, down, right, left. We tilt it so that the x-axis is on the ramp, parallel to the ramp. And then, if the object is stationary, moving with constant speed, we use up equals down, left equals right. And if the object is accelerating, we just use Newton's second law. So here's a ramp problem. Give this one a try and play the video after you've attempted actually 1, 2, 3, all three ramp problems. Okay, you should have attempted these ramp problems on your own. Let's go through them. So here we have a ramp, a block on a ramp. We know the weight of the block is 20 newtons. It's allowed to slide down the ramp. This doesn't say anything about friction, so I'm going to assume frictionless. And what we're going to do first, always, is draw a free body diagram. So what I like to do is, before I start my free body diagram, draw a dotted line to represent the ramp. Draw my block. And we have a weight force, mg, and we have a normal force that's perpendicular to the ramp. No friction because the problem didn't mention anything about friction, so I'll leave that out. Now, what we do with ramp problems is we tilt our coordinate system. We make the x-axis parallel to the ramp, and we make the y-axis, this is now my y-axis, perpendicular to the ramp. This makes the problem easier. Okay, what we do from there is we break down the weight into components. So I'm going to break the weight into two components. one pointing down in the new coordinate system, one pointing left in the new coordinate system. Cross out the weight. This angle, the angle 37 degrees, is right in here. 37 degrees goes in the inside this sort of triangle that I just made. This makes this component mg cosine of 37, this component mg sine of 37. Up equals down, normal is my up, down is mg cosine 37. Okay, I'm looking for the normal force. So the normal force equals the weight, which is 20 newtons, times the cosine of 37. If you don't know this, you can look it up in your table of information. I'm just going to use this triangle here. Cosine is adjacent over hypotenuse. 4/5. Multiply, you get 16 newtons. Let's try this ramp problem. Now we have a block. It's sliding down this 30-degree ramp, but it's accelerating at 2 meters per second squared. It's got an acceleration. Okay, first things first, free body diagram. Weight mg, normal force n. I like to draw a dotted line for the ramp so I can tell that this is perpendicular. And friction force opposes motion, force of friction. Okay, so this is looking good for our free body diagram. Now we want to find what is the frictional force. So I'm gonna draw more of a working free body diagram so you can see the detail. Here's my block. The weight mg, normal force n, and friction force F of F, opposing the motion. Remember, we tilt our coordinate system. Now this is the x-axis and this is the y-axis. Then break the weight into components. This is why we tilt the coordinate system, so that we don't have to break two forces into components. We only have to break the weight into components. So break it into a vertical component and a horizontal component. Cross out the weight. I just replaced it with its two components. This angle right here is 30 degrees, which makes this mg cosine 30 and this mg sine 30. Okay. We're looking for the frictional force, but I have to remember that the block is accelerating. Okay? Accelerating means I have to use Newton's second law. F net equals ma. The net force here is going to be left minus right equals ma. It's accelerating down the ramp, so I know the left force must be bigger than the right force. The left is mg sine of 30. The right is the force of friction, and that's equal to m times a. The weight mg, so the weight is 2, so that's going to be 2 times 10. Sine of 30 is a half, minus the force of friction equals 2. The acceleration is also 2. Solving for, let's solve this real quick. 2 and 1/2 cancels. We get 10 minus 4 equals the force of friction, where the friction equals 6 newtons.